Moving coil galvanometer. Moving coil galvanometer is used to detect the presence of small electric current of the order of 10 to the power minus 9 ampere, and it gives the direction of current also. Suppose I have a circuit, I am considering a part of circuit and connected a galvanometer in it. When a current is flowing in this direction, the galvanometer may show the deflection in this direction. If the direction of current is reversed, the deflection of the galvanometer also reverses. As a result, it detects or finds the direction of current also. Then what is the principle behind the galvanometer? As we studied it in the previous video, a current carrying coil placed in a magnetic field experiences a torque. This is the principle behind the moving coil galvanometer. So if you place a rectangular coil, any rectangular coil or any current carrying coil, if it is placed in a magnetic field, it experiences a torque. This is the principle behind the moving coil galvanometer. And the amount of torque experienced by a coil is proportional to the current flowing through the coil. We studied it in the previous video. Just have a look at that and later you come and watch this video. The torque experienced by a rectangular loop is given by, we studied it, torque tau is equal to mb sin theta. M is magnetic moment, and the formula for magnetic moment, I will write it here. M is equal to I into A, right? Where I is the current flowing in a conductor, flowing in a loop, a rectangular loop, and A is the area of cross section of the loop. And if there are n number of turns in it, you can multiply n also for this. So that's what I'm going to write here. So M is equal to NIA. So magnetic field M is equal to NIA, and remaining B sin theta as it is. Here in the figure, in this particular figure, the arrangement is made such that the angle between theta, the angle between the magnetic moment and magnetic field is 90 degree. So here in the diagram, the detail of this is not there in your syllabus, but only little whatever it is required I will tell you. So here the magnetic field direction is something like this. This is the direction of magnetic field, and the direction of magnetic moment is always perpendicular to the plane of the coil. As a result, the angle should be 90 degree. So theta is equal to 90 degree. Here you see the coil. The same diagram here it is there. And this is the top view of this particular diagram. This is the top view. So there are many number of turns wound over a ferromagnetic substance, soft iron particularly, that is there here. This is a soft iron, and there are many number of turns, rectangular turns. Here you can see these are many number of turns wound over the soft iron. So this diagram that is. So the magnetic moment is always perpendicular to the plane of the coil. By using right hand thumb rule, we will get that EM. And magnetic field is like this. The direction of magnetic field is shown here. So that is why we are using such type of magnet produces a radial magnetic field. Okay, the detail of that is not included in your syllabus. So now you only understand this particular thing, whatever required. Theta is equal to 90 degree. Therefore, NIAB, you are going to get NIAB, that is torque. So as a result of torque, what happens? This torque deflects the coil through an angle of theta. So this torque, this coil experiences a torque and a rotate angle theta. Once it rotates, what happens? So it is just like a spring. I have a spring, and if you rotate the spring, don't stretch this spring, just rotate it. If you rotate, what happens? It keep on compresses, right? It keep on compresses like this if you rotate it, and the length shrinks. Once a stage is reached, what happens? The spring acting itself acts as some opposite force, that is restoring force, and that restoring force is again a torque, a rotational effect. The restoring torque will be developed inside a spring, so as a result it comes back to its original position, how it was there. And this restoring torque is set up in the coil due to the elasticity of the spring. That is a spring inside the moving coil galvanometer. So that restoring torque is again proportional to theta. How much you are rotating, the same amount of torque will be stored in it, the restoring torque. And that restoring torque is equal to k times theta, where k is a constant. It is just like a spring constant in a rotation. This is called as torsion constant. So at that particular stage, the restoring torque is equal to the deflecting torque. Both the torques will become equal. So k theta is equal to NIAB. So this restoring torque and this torque both becomes equal, and equate them. So now in your syllabus only this much is there. Mention the expression for the deflection of the galvanometer, that is deflection torque. They are asking theta. Theta is equal to NAB divided by K times I. Here some constant, this constant we represented by NAB divided by K as 1 by G. So finally theta is proportional to I. This is just a constant, leave it. Therefore theta is proportional to I. That means what? Greater the deflection showed in the galvanometer, that means the greater amount of current is flowing through the galvanometer. And that G is called as galvanometer constant, that is J is equal to K divided by NBA, is a constant of galvanometer, and it is also called as figure of merit. Then what is figure of merit? The figure of merit, it is defined as the current which produces a deflection of one scale division in the galvanometer. That means I have a galvanometer here. It consisting of many divisions. The galvanometer, actual galvanometer, has zero deflection at the middle, and on each side there are some divisions like this. So this is 0 point in the middle. So now you pass the current through a galvanometer. Just pass a current in it. So after passing the current, it deflects. It may deflect somewhere here. One division it will deflect. And the current required for one division deflection, that is called as figure of merit. So current required for one division, that is called as the figure of merit. So I divided by theta, current per unit deflection, that is called as figure of merit. So here G is equal to, we can write the same thing, you reverse it, K divided by NAB you are going to get. This is a figure of merit. The current required for one division deflection, that is called as figure of merit. Now there are two sensitivities of the galvanometer. One is called as current sensitivity and one more that is called as voltage sensitivity. What is current sensitivity? The deflection produced in the galvanometer when a unit current flows through it. That is called as current sensitivity. If you pass a unit current, if you pass 1 amp of current, 1 milliamp of current, or 1 unit current through a galvanometer, then how much deflection it shows, the galvanometer shows, and that is called as a current sensitivity. So current sensitivity is deflection produced per unit current. Deflection produced in a galvanometer for unit current passing through the galvanometer, that is called as current sensitivity. So NAB divided by K. So theta value already we found it, right? Theta is equal to, here it is there. So NAB divided by K times I. So I and I will be cancelled here. You will get this one. Then what about voltage sensitivity? So deflection produced in the galvanometer when a unit potential difference applied across its ends. So I have a galvanometer and apply a potential difference of 1 volt. I have a galvanometer here. I will apply a 1 volt potential difference across this 1 volt. Then it will show some deflection. It may show some deflection, and this deflection produced per unit voltage, that is called as voltage sensitivity. Okay, theta divided by V. V is potential difference, and that potential difference is I into R. But theta is equal to, as we know, theta is equal to NAB divided by K into I. Use that. And I will be cancelled, and you will get NAB divided by KR. So this is a voltage sensitivity and current sensitivity for 2 mark. They will ask, what is current sensitivity? Deflection produced per unit current. And what is voltage sensitivity? Deflection produced per unit voltage applied across the galvanometer. So it is found from the above equation that voltage sensitivity is current sensitivity divided by R, because you see this term is just I, current sensitivity. We found it from the current sensitivity.